So just looks like today a lot of people are talking about the Microsoft App Challenge. So this is a little bit more in detail about what goes on behind the scenes, behind all the cool graphics. So I'm going to be talking about extreme code optimizations in computer gaming AI. So this is when you're playing a computer in chess or checkers or other interesting games like that. So the area I'm looking in is called abstract strategy games. So these are games that there's no elements of luck, so no dice or shuffled cards. And there's no hidden information, so there's no cards or information that are out of use, so like Minesweeper or Solitaire, abstract strategy. So it's generally a finite number of alternating turns, so black will move, white will move, and so forth. And this is the key point. Theoretically, for every position, there's going to be some correct move so that you could either win or avoid losing, or if you're going to lose, there's going to be a correct move to delay losing as much as possible. So chess maybe, or maybe there's some kind of counts at the end, maybe mercy of dollars. You want to lose as little as possible. But of course, there is a correct move to the first move to chess, but it can take a very long time to compute. So it's generally two-player games. There's some one-player abstract strategy games like Sudoku or Free Cell, or moving block games like Klonsky. And I guess you could be interested in writing some kind of a program to solve these games. But generally, those are within NP, so at most NP complete. So if you have a good reduction from any of these games to SAT, most SAT solvers will crunch them right away. There's also multiple player abstract strategy games. Chinese checkers can be played with 6 players, and my guess is you can probably adapt what I'm going to say to things like that, although I haven't been working on Chinese checkers or any games with more than 2 players yet. So some examples, Reversi, Othello, chess, and there's some variants of chess. I wrote mini chess, and there's variants of chess like shogi, where after you capture a piece, it becomes your own. So this is to show when you put your pieces that you've captured, and during your turn, instead of making a move on the board, you can drop a piece that you captured onto the board as your own. So that you're actually capturing in shogi. Any kind of Connect X game like Connect 4, and of course I think everybody likes Go, but that's actually quite difficult for computers to play. We'll see why later on. So how do computers strategize? So if you look at a position, like for example, some position in Reversi, you're probably going to think along the lines of, okay, I have 5 different moves that are available, and if I make move A, my opponent has 5 other moves that are possible. You know, after A and D, I can choose between, so forth. So it's like a tree of different possibilities, and you're probably going to assume that your opponent's going to make the best moves that he can, and what you're going to do after that. And it turns out computers think not too differently. So the computer's going to find a move that maximizes its position, but it's going to assume that you find a move that maximizes your position, which means it minimizes the computer's position. And at some point, unless you want to solve the game and search all the way through to like a checkmate position, you're going to have to cut off somewhere and say, okay, 10 moves later it's going to look like this. What's the value of that position 10 moves later? And you would have to have some kind of function to give you a value for every position. Basically a guess of how good or bad position is based on various factors. So an example for tic-tac-toe, a pretty trivial example would be, let's say you're evaluating this in X's perspective. You might say, okay, let me look at how many lines I have available still to win. And let me look at how many my opponent has left. So here, X has 2 lines left. It has the right side and the bottom. And O has 3 left. It has the diagonal and the 2 middle lines. So I might say, okay, this position evaluates 2 minus 3, because the lines that X has left are good, because X is trying to win. And the lines that O has left are bad, because then X loses. So I might assign a value of -1. And keep in mind it doesn't just take the position it's working on, it says, okay, -1. What it does is a search, and maybe if it can search 5 moves ahead, it gives every position 5 moves ahead a number, and then it crunches that by making an assumption that everybody's going to make the best moves later on. And so this was actually the example that I found in the very first paper on Minimax searching, and it's beautiful because it can be extended to other games where you're connecting. So connect 4, how many lines do I have left to connect 4, and it actually plays pretty well if you use a heuristic like that. And it's pretty easy to compute, as we'll see. It's actually a lot easier than you might imagine using loops or anything like that. So an example of what the structure of a Minimax search would look like is, well, you don't know these numbers when you begin. This is the combination of this stuff. But you get to the leaves. So let's say you want to search 3 moves ahead. You compute a value for all those 3 moves ahead. And because this is black's turn right here, let's say big numbers favor black. So we're going to assume black is going to choose the biggest of these numbers, and the biggest of these numbers, and the biggest of that. And white is going to try to minimize because smaller numbers favor white. So we're going to assume white chooses the smaller of these, which is the smaller of the bigger of these. So that's why it's called Minimax, and so forth. So you're going to have one layer of maximizing, one layer of minimizing, another layer of maximizing, and so forth. So this will tell you the value of that. And if you're playing black and you're deciding between these 3 moves, you're going to see this has the highest value. So you're going to play whatever move this edge is referring to. But there's some inefficiencies that come up. So for example, there could be multiple ways of reaching a position, and if there are, you could be repeating searches, and that's pretty bad because if, let's say, this and this were the same, well, actually, maybe this and this one, then whatever goes on here is going to happen multiple times. So that's definitely something you want to avoid. So, for example, in that chess position, the order of any of those pawns and knights could have been different. So that's a very huge number of different ways to reach that position right there. So you would want to store up the value so you can just recall it later. And that's called using the transposition table because the moves can be transposed. And in some cases, it's easy to see early on that some move A is no better than some move B. Like, for example, if I make a move and there's a response my opponent can make that instantly checkmates me, I don't have to check the other responses of my opponent because I already know that's a bad move. So the technique to get rid of those moves is called alpha-beta pruning. And an example, we'll just show you the same example. What will happen is white's turn over here, and he tries this move, and then he can try this move. But black already has a response that beats this alternative, so we can get rid of this whole tree because you really can't. Even if these are better, white's gonna choose something good, so you don't want to play this move. This one, the first response is not as good, so you still have to check out the second one. The same thing happens here. Here 7 is already better than 5, so we don't have to check out what this yields us. And here 1 is already worse than the 5, so we can get rid of all. So you can get rid of more as you go on, because you have more information on what happens with the scores. And as you can see from that last example, if you find a good move early on, you prune a lot of trees later on. So this works best if the best move is tried very early for each position. But obviously, you don't know what the best move is before you actually search. So there's some heuristics you can try. Obviously, a good approximation of the best move is to try a shallow search first. So we didn't show it here, but each of these positions, besides this minimax value, is also going to have an evaluating value. So if we evaluate these 3 positions first, and we chose the one with the highest score, we could reorder the search tree, and maybe we might happen to search this 5 node first, and that would increase the pruning by quite a bit. guarantees, obviously, because a shallower search is going to be less accurate than a deeper search. Another alternative is iterative deepening. So you search one ply first, ply being one move from one side, and then you try 2 ply and then 3 ply. The reason you do that is not only do you get an ordering for the top node, you get an ordering for every node that happens on the way down because of the recursive nature of alpha-beta pruning. So in theory, in the best case, if you happen to try all the moves in the right order, you can search roughly twice as deeply in the same amount of time as you could with straight up Minimax. Obviously, you're not going to always try the right ordering. If you did, you wouldn't need alpha-beta pruning, so usually 1.5 times is a good approximation. So there's some problems with alpha-beta pruning. Believe it or not, the alpha-beta pruning is going to spend the majority of its time on a number of things that you might think are trivial. So checking whether one side or another has won. The reason this is very time intensive is that it's done on every node. So every time you make a move, you got to check if one side has been checkmated and if something has happened, or if there's a repetition, like in chess, if you repeat the same position 3 times. So that's done a lot. Even though each operation might be tiny, that's done a huge number of times. The evaluating functions are done on all of the leaf nodes. And because this is an exponential tree, the leaf, that's going to be the majority of the nodes. The operations in making the move, those are the connections between the nodes, basically. So if I'm doing alpha-beta pruning on this node, it's going to have to execute each of these moves, and that's considerably time-consuming because it's done so many times. Finding all the legal moves, so this is not a trivial task in a lot of games, especially for reversing, because you have to check how all the pieces interact with each other. And then there's loop efficiencies when you're trying to iterate over the legal moves. So this is internally within the nodes, how you're iterating all the legal moves in order to try them all out. So there's also space complexity issues of storage of the game position. So because remember the transposition tables, and also when you're doing recursion, what happens on the stack, especially if it's a very deep search, there's some storage issues. And it's indirectly crucial because the more space you have for the transposition table, the more entries you have to store transpositions. So you're saving time indirectly that way. You're not going to save time per node, but you're going to be able to search a lot more. You're going to be able to search a lot deeper for the number of nodes that you're searching. So it's a different kind of efficiency that's being involved here. Another problem with alpha-beta pruning is the branching factor, i.e. the number of legal moves at each position. So up here, there's, assuming this is the complete tree, there's 3 moves that are legal to this node. So you can imagine if every position had 100 legal moves, this could blow up very big, 100 times another 100, and so forth. And that's especially a problem with games like Go, which I'll talk about. So the higher the branching factor, the less we can search. And it's actually a double whammy, because not only does the number of nodes blow up very fast, but each node becomes that much more complicated because you have to generate so many different moves and iterate through them. So it's a double whammy in that sense. So typical branching factors for Connect 4, it's obviously at O7, there's 7 columns, and it turns out Connect 4 has been solved in large part because of the small branching factor. You could probably write a program to solve it today. We solved it 30 years ago. Reverse C, there's probably 10 legal moves in the middle game. And computer reverse C is often orders of magnitude better than the best grandmasters. Like you could probably download a game that's better than the champion, like online. It's just like incomparable. So most experts believe that reverse C will be solved in the coming years, and it's presumably a draw under perfect play. Chess, you got 30 legal moves, give or take, in the opening and the middle game. And if you recall Deep Blue versus Kasparov, maybe 10 years ago, computer chess is roughly equal to the top chess players today. And also, there's been some myths in chess that white has a huge advantage, and computer analysis has somewhat dispelled some of those this as well. So we're developing opening strategies with computer analysis as well. Go is the challenging one. Even for 9x9 Go, the breaking factor is already at 50. So even if you have perfect alpha beta pruning, the square root of that is still like 7. So 7, it doesn't take very many powers of 7 before you blow up. So and that's just for 9x9. Usually you go for 19x19 or something like that. And we've solved 5x5 Go. That's as far as we can get. So 5x5 is 25 different legal moves on the first move. So square root of that is 5. That's still somewhat doable. Pluses and fours builds up, fewer options available. So that's still somewhat doable. Shogi, this is the chess game where you can drop, capture pieces. It has a huge branching factor because when you drop a piece, almost all the empty squares are going to be legal moves. But it's actually not so bad because it's pretty easy to evaluate functions, evaluate the position, because it's mostly just material where we're playing chess. If you're going to drop a piece in a very illogical position, like where it could be immediately captured, your alpha beta pruning is going to pick that up very quickly and eliminate most of those branches. So actually there's a 3x4 variant of shogi where you can also drop pieces, and that has been solved, and it's counterintuitive because the second player can win, and it actually takes up to 81 moves. So we talked about the double whammy involved. The high branching factors not only blow up the number of positions that are available, but also individually on each node, there's a huge number to loop over, to compute. So another bottleneck is evaluating the position. So if your evaluation, there's a trade-off. You can have a very simple evaluation function and hope that your depth will take care of the mistakes it makes. So if you're searching basically almost all the way to the end of the game, you can probably get away with a not so good evaluation function. If you make your evaluation function really complex, you're not going to be able to search very far. So that's a trade-off. So in games like Reversey, the value of a position can be extremely sensitive, meaning that a small change in the board will change its true value, i.e., who will win and by how much under perfect play significantly. So these two positions are only different by one square, but if both sides play perfectly from here on in, black will win 44 to 20 over there, and only 33 to 31. There's a difference in 9 just from changing one cell. So very sensitive game. Another bottleneck is in some games like Go, just to determine whether or not a set of stones is going to contribute to the final outcome, whether or not it's alive, is already empty hard. So you can imagine if that's going to be a subroutine of your algorithm that's already empty hard on top of that empty hard, that's going to blow up. And then you have some games like chess where intuitively you would think that having it being your turn is an advantage, and it usually is, but there are quite a number of positions where it's otherwise. So in this position, if it's black's turn to move, he has to move his king over here, and then white can bring his king up here and promote his pawn in the next move. If it's white's turn, he either moves his king away from the pawn and black captures it, or he moves it here and it's stalemate. So there's positions like that throughout. We just talked about how in Animal Shogi that the second player wins. So this is already one of those positions where it's a disadvantage to move. I don't know how to pronounce that word. It's Zwang or something like that, when this happens. So it's very counterintuitive when you have something like that. One way to get around some of these inefficiencies is by a concept called bitboarding, where you're storing a lot of information about a position as bits of an integer. So if we're playing Reversey and there's 64 cells, all of the cells that black occupy, that subset of cells, can be represented as a 64-bit integer. So I just basically wrote out that 1 represents that So this is a 64-bit integer. And similarly, you can do the same thing with white. So this is not only is it space efficient, but we'll see it's very time efficient when you're doing some of these operations. So it's obviously very compact compared to like an array of some sort. And it's very fast because you can learn interesting information about the gate position in just a few operations. So if I want to say, I want all the squares directly north of black disk, we could just shift everything by 8 if we're representing it this way, because then all of the numbers will move up by one row. And that's just one operation as far as the computer is concerned, because shift is one instruction. If you were to do this with an array, you would need basically 64 instructions to move everything up by one index in the array. You can do things like get all the black disks directly adjacent to the white disk. So this is actually pretty important because if you want to do a capture of some sort, or you want to compute the mobility of a player, which is obviously important when you're evaluating the position, this is actually a pretty common subroutine. You can just shift everything by one space in all 8 directions, and this and will say, okay, not only is it adjacent, but there's a white piece there. So it's not quite actually, because when you're shifting by one, some of it wraps around, so you need like a filtering constant to and that with. But you get the idea. It's one instruction like that. If you didn't have it represented this way, you would have to write 8 different loops of instructions to do all the 8 different shifts and do the AND operations. And that's like thousands of times less efficient. So you could also execute moves this way. If you want to flip the 3 pieces directly north of X, so you're doing a capture, you put that into an integer Y, those 3 positions, and you flip them with an XOR operation. XOR equals Y, and that will flip all those disks from 0 to 1 or 1 to 0, or vice versa. And it lends itself very well to parallel computation. Because you want to find all the legal moves in the reversing position, for example, and X left shift by 8 will find all the pieces to the north at once. So you're basically doing the whole board in parallel when you do this. Modern processors are very fast with 32-bit and 64-bit integers. So 32-bit is used, I used it for American English checkers. This is the checkers you're probably used to. It's on an 8x8 board, 32 spaces, so that will represent all the pieces on one side. And it also represents sets of squares that we might be interested in. So for example, all of the squares that X can move to can be one integer, for example. You can do small chess variants. There's a mini chess that's played on 5x5, and then there's a micro chess that's on 4x5. And Clobber, which I'm also writing, is played on 5x6. And all those are within the 32. 64-bit is obviously very useful in chess, which is played on 8x8. I'm still working on that. Reverse Othello, we just talked about that. And Polish or international checkers, which is played on a 10x10 board with 50 spaces. So as an example, we can go back to tic-tac-toe. If we represent all of the squares X is on as a 9-bit integer, do that with Y, or with O as well, and we call them pieces X and pieces O, and these are 2 9-bit integers, we can do a lot of computations, like the evaluation, very fast. So for example, I want to see how many lines X still has available to win, or rather O actually. Then I invert pieces X, that will give me all the cells that are either empty or O, and then I have to see how many lines are in that. So if I take the AND of all the things that are not X, I shift that by 3, basically down 1 row, and I shift that by 6, basically down 2 rows, and I take the AND of that, that'll give me all of the lines that have no X's in them at once, and then I can count how many bits that is. And I can do that for left and right as well, and I can do that for diagonals. Those become different shift numbers, obviously. And notice that we count that in one operation. We don't have to have loops going through the rows. If we did that as a loop, we would have to loop not only column by column, but row by row as we sum them up. So this is basically parallel computation hack. So as a more complicated example, here's the structure I used to represent international or Polish checkers. All of the pieces can be represented, all the black pieces is one unsigned long, all the white pieces is another one. Unsigned long is how you access 64-bit integers on a 32-bit platform. It does some kind of hack to do that. And then all the kings on either side can be represented as one. So basically, 64-bit integers can represent subsets of that board. It doesn't have to be all the pieces or anything like that. So the last piece to make a jump, that's interesting because in checkers, you can make multiple jumps in one turn, so you need to keep track of who's doing the jumping. Then jumped is to keep track of which pieces have already been jumped and have to be removed after the turn is done. So in Polish checkers, unlike American checkers, when you jump a piece, you don't remove it immediately. The difference is that you can't later jump, let's say you have a piece beyond that jump piece, and later your path crosses it, you won't be able to jump this piece here because you remove the jump pieces after your entire jump is complete. So it's a little bit different. So you can see these are very versatile. You can represent all kinds of subsets of squares using integers by using the bits as the squares on the board. So some interesting hacks that come up often. Let's say I have a square on the board and I need to get its coordinates for some reason. For example, to make a move. So basically, I have 2 to the I, which is one left shifted by I positions, and I want to get I back for some reason. By Fermat's little theorem, we know that for I from 0 to 63, 2 to the I mod 67 is going to be distinct. So we can compute x mod 67 if we know x is a power of 2, and we can look up that result in a table. And the caveat is division is somewhat slow. But that's still a lot better than having to do any sort of looping. Another interesting bitwise operation you might want is to get the least significant bit of an integer x. So in 2's complement, if x is this integer right here, and you take minus x, that's going to give you basically the negation of x plus 1. And it's going to look like something like this. And if you add the 2 of them, you actually get the lowest significant bit. And this is interesting because this gives us a means of looping through all of the bits. So now we can subtract this y from x, and then we can continue until we get down to x equals 0. So this gives us a means of looping through all. So if you imagine x is like all the legal reversing moves, and you want to loop through them, this is a very efficient means to loop through all the ones in a 64-bit integer or 32-bit integer or something like that. There's some other interesting hacks. You can find the most significant bit. It requires slightly more work, so if you're just interested in looping and you don't have a reason to start from the most significant, usually you'll use the least significant. You can count the number of bits in an integer. For example, it might be useful to count the number of pieces on each side or count the number of legal moves. And this is called Hemming distance, when you count the number of bits that are set to 1 in an integer. And you can define masking integers such that each bit of a certain type is set to 1 and the others are 0. So an example of why you would want to do this is maybe you want to say, how many white chess pieces control the center 16 squares? Then you could take the bit that the integer that represents the central 16, and you can AND that with the white pieces, and then you can count how many bits are in that. So that becomes just a series of maybe 5 operations at most. Of how many white reversing pieces occupy the corner. So the reversing corners are very important. That just becomes the white pieces and the corners integer, and count that number of bits in that. So that's 3 operations there. Some other interesting hacks for bitwise is, let's say you have some priority for
moves you want to try. So in reversing, I just mentioned the corners are the most important. The X squares, which are the squares directly diagonally across from the corner, are bad, because usually if you take these, your opponent can probably take the corners. And usually besides that, the middle pieces are good. So this might be the priority of the squares you want to try that in. And you can implement that by having each priority level being one integer. And now you can say, okay, if X is all the legal moves, I'll try X and X1 first. That will set all the bits that are at priority 1 and also legal, and so forth up to X of 9. And so this gives some kind of priority to the moves to try. You can do multiplication and division by constants, especially powers of 2, by shifting very easily. I think most people know that. It's actually done automatically by computer optimizers, compiler optimizers, I should say. So if you write, for example, y equals x over 4, the compiler is probably going to automatically change that to y equals x, right shift 2. And in fact, it often pays in your evaluation function. Let's say in your evaluation, you logically really wanted to divide by, I don't know, 65. Sometimes it pays to be a little less accurate and say divide by 64, even if it's logically weaker, because it's so much faster, you can search deeper to make up for that small error that's being introduced. So sometimes it pays to approximate things as long as it makes the shifting and the automatic optimizations a lot faster. So another problem with alpha beta pruning is that you have to cut off at some point. But what if that position is somewhat unstable? So for example, the search could cut off right when the tables are about to turn and the losing side is about to capture a big piece or something like that. And this is called a horizon effect, because this is a horizon that you're seeing, and perhaps there's something big beyond that horizon. So here, black is about to lose this bishop. It's trapped behind here. White can move the king over to the capture, and this happens about 8 ply from now. So in theory, black's best move is probably to capture this pawn and get it done with right now. But if black is looking 8 ply ahead, they can kind of forestall the loss of the bishop by moving this pawn up, because now white has to capture, and it doesn't see that 10 ply later it's going to lose its bishop anyway. So if it's searching 8 ply, it would probably make that move, and then white would capture. And then if it searches 8 ply again, it would probably move this pawn up to forestall the capture. So it's making very suboptimal moves because of the way the cutoff is being applied. So the idea is to avoid cutting off the search at loud moves. So for example, a typical loud move might be a pawn move, for example, especially if it involves a capture or a promotion. Most captures are probably loud. You've got to see if your opponent can recapture or do anything else. Moves that result in a major gain in mobility is probably questionable. Like, you want to see, is that really that good of a move, or is it a trap? Any kind of forced move, so a check that can be only answered in 1 or 2 distinct ways. It's always a good way to do these, because if it's a forced move, your branching factor is going to be low, and it's not going to add very much to add to the search depth when things like these come up. And you got to be careful not to have an infinite loop. So for example, if you add to your depth every time you make a capture and you're playing shogi, that could be an infinite loop, because you could have capture, drop, so forth. So you have to be careful how you implement that. You could have a maximal, for example. I can extend certain positions, but I'm never going to go more than 3 times my initial depth or something like that. And in my implementation mini chess, what I did was I basically just avoided stopping the search following pawn promotions and captures. And it's impossible to have an infinite number of those, because you have a finite number of pawns to promote and pieces to capture. So it worked out very well, and I lost a lot of noise in terms of the alpha beta values. And these ideas actually affect how we evaluate positions. So for example, in checkers, if we always avoid ending the search after a capture, and we continue if a capture is available. And that can't loop because each capture will reduce the number of pieces available, obviously. Capturing is also mandatory in checkers. So these conditions, they tend to eliminate each other. And it doesn't actually extend very much. And so if we always continue when those cases happen, at the leaves of the search, we're not going to have any captures available, and the last move is not going to be a capture. So our evaluation function can avoid considering any immediate captures. So that simplifies the evaluation function, actually. So this is a very beautiful concept to apply. So for reversing, some interesting techniques are to avoid ending the search. You should probably not have the last move be a pass. That's usually a sign that the game is kind of unbalanced in some way. Things can be flipping around. If you have forced moves where you only have one or two legal moves or you're passing, that's probably a sign that things are about to change. Any moves to unresolved corner areas, if you make a move to the X square and the corner is empty, you might want to check if your opponent can move there. And changes to the status of a diagonal. So in reverse, the diagonals that go from A1 to H8 and A8 to H1 are often very crucial to the outcome of the game. And I'm going to show you an example. So let's say you're black and you see that white has placed a piece on the X square, but you can't immediately capture that diagonal or that corner. So what you might want to do is called cutting the diagonal. So you try to capture one of these pieces in the middle of the diagonal. So now black goes here, and now the corner is available. So white will want to break that cut as well. So white might go to C2 and take that diagonal back, and then black can cut at C5 again, and now there's no way for white to recapture. So things like that, you don't want to end your search in the middle like that, because then you might not know that black already has that diagonal, that corner in a few moves. So any major changes to the status of diagonal. So there's three different kinds of ways. There's three different ways a diagonal can end up. It could be a solid one color like here. It could have two colors, so maybe you have white, 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 black, black, for example. Or it could have one color that's sandwiched in between the two, like I just showed you. So this would be considered a loud move, because you're going from one configuration to another, and then you're going back, so you might want to search one more move after that, and then another. So if you search one more move after that, you would realize that black has already won that diagonal. So some results from these concepts I want to show you guys. And all of this is just from running it off here. There's no specialized hardware or very fast processor or anything like that. For 8x8 reverse Othello, I was able to get about 800,000 nodes every second. And the typical search, even including the endings, you don't want to end with loud moves, the quiet moves, heuristics. I was able to get 10 to 16 ply, depending on the state of the game. In the opening is pretty deep. And the end game is also pretty deep. In the middle, when you have a lot of legal moves, is when it's pretty shallow. And this, I'm talking about reasonable amount of time, maybe 30 seconds to move. So this is low branching factor, but relatively complicated moves and legal move computation because of the way the pieces interact with each other.
Question for you?
Yeah.
So the game is variously known as Go or Wei-Qi or Badger. Could you model the 9x9 variant with these techniques?
Oh, of course, yes. It's a lot more complicated though, because first of all, the moves and the captures are pretty complex, right? Because you got to search the group, right, and see if it's completely surrounded.
Yeah, you need to know groupness.
Yeah, and life and death. This is something that comes up in the evaluation function. Is NP complete.
Yeah.
So you have something that's NP complete within a search that's already NP complete. So that seems pretty bad. And I think if you were to try to solve Go, it's X time complete or something like that.
Yeah.
So Animal shogi is a variant of shogi played on a 3x4 board. It's been solved, but I wrote it as an exercise, as a stepping stone to get to other shogi variants. It has a relatively high branching factor, actually, for its size, I mean, because of the drop moves. But it has very few distinct positions, so your transposition table kind of kicks in right off the bat. So it's not as bad as it seems. Like, you look at the branching factor, it's like 10, but it's all the same thing, so it's not as bad as you would imagine. There's also a micro shogi, which is played on 4x5, similar flavor, huge branching factor, but a lot of repetition going on, and so it's not so bad. Clobber is a game that's similar to checkers, except it's played on an orthogonal board. It has a huge branching factor in the opening, because right off the bat, almost all the pieces can move, but the generating the moves is very fast. The legal moves computation is very fast. So you can search lots and lots of nodes per second. The only downside is the huge branching factor significantly reduces how far you can search. And it's kind of hard to evaluate as well. Mini chess is played on a 5x5 board. I think I showed a picture earlier. 10 pieces on each side. I was able to get about 1.5 million nodes a second, and I got to about 10 ply, and even deeper in the end games. It's presumably a draw. It hasn't been solved. The interesting thing is, if you write chess, especially at a competitive level, you need huge endgame table bases to find checkmates that are somewhat complicated. Like, you can checkmate with a knight and a bishop and a king against a king, but because it can take, like, I think 68 ply in the worst case to do it, you're not going to find it just by a regular search. You need some kind of a database. If this position comes up, I make this move and so forth. That's pre-computed and stored somewhere. And I was able to find all of the knight and bishop checkmates without one on the 5x5. So it's significantly less complex than 8x8. For 8x8 chess, which I also wrote, I didn't write the table base. I was able to get 200,000 nodes per second in the opening, and roughly the same as mini chess for the end games. So the real complexity was the sheer number of pieces and legal moves in chess. It wasn't so much the complexity of chess itself. I also wrote American checkers, Polish checkers. Polish checkers has pieces that move long ranges, and that added quite a bit to the complexity. It's only able to get about 10 plots compared to 14. The thing that saved me is that because of mandatory capturing, you basically have lots of nodes with very small, usually 1 or 2 branches, because you have to capture it. Maybe there's 2 captures. That's still pretty small. Actually, American checkers has been solved, and my program didn't get as far as solving it, but you could see that it basically reached an endgame just from the first available move. Some things I want to try, I got to get 128-bit integers to work. That way I can implement things like 9x9 Go, 9x9 Shogi. There's Chinese chess. Hex is usually played on 11x11, so 128-bit will cover all that. Right now the library I have is pretty slow, so I'll have to look at some implementation for that that's suited to what I'm trying to do. We might be able to cut off some of the bad moves without having to try them. If you recall alpha-beta pruning, you still have to find one line of reasoning that refutes your move, but most humans will, if you see a move that's already bad at 2 ply, you're not going to try it at 7 ply, for example. And even alpha-beta pruning still has to go to 7 ply to say, okay, this is bad. It might not do all of the moves at 7 ply, but it still has to do something at 7 ply to say it's bad. And then we, for solving things like 5x5 mini chess, this is most likely going to be done with, we got to generate those endgame databases. So the result of all the positions with less than X number of pieces on the board, or maybe all the positions without pawns, That way, if we reach an endgame position, we say, okay, white will win this position without having to go further down. So basically, we're working our way backward from checkmates and also working our way forward from the initial position and seeing if we can meet in the middle and solve the game that way. This is difficult for games like shogi because you really don't have an endgame in shogi because of the drop move. So if you can do alpha beta searching all the way to the ending positions in the database, then you basically solve the game. So, and I estimate there's about 10 trillion positions in 5x5 mini chess. So the U.S. national debt is like 16 trillion. So if there's a position for every dollar of debt the U.S. has. So if you want to try out my games, I have a website. The project is called Deep Nikita. Website deepnikita.webs.com. Want to try it out? I have all these games that I list, and a few more less common games that you guys probably wouldn't know about if I talked about here. Questions? Anybody want to challenge?
I didn't realize American checkers was solved. When was that? When did that happen?
2007, I think.
Okay.
Yeah. I think it got up to like quadrillions of nodes. I mean, it was a parallel computation, so my program only gets up to like trillions of nodes even within a few days, so I'm still quite a ways from catching up to what somebody else has done for checkers.
Okay.
Yeah, I think if I were to rate some of the, well, my chess program is very novice. I mean, it'll bring out the queen out on the third move, so I'm still working on that. It's only getting up to 4 or 5 on the first position, but reversey, it plays at an expert level. I don't know if it's going to beat the world champion like how most top reversey programs do, but it plays at a pretty top level. I've used it on playing people on Yahoo games, and I've never lost. So, and I usually wipe them out. Shogi is the small variants of shogi. Nobody really plays them, so I'm not sure, but it can usually find mates in like 10. So I'm assuming that it's finding other good moves at 10 as well. So yeah, so try it out. Anybody here play international or Polish checkers? I'm surprised it's called international because I've never seen it. Only when I started working on these games did I realize there was another variation of checkers floating around. No? All right, well, yeah, check out my games if you get a chance.